The last presentation of this section is Kahnu Charan Pradhan, probably pronounced terribly. You can correct me afterwards. From the Department of Chemistry in Bhubaneswar, India. He is a PhD student, and he will talk to us today about cyclometalated iridium complexes as phosphorescent emitters. Thank you very much.
Sir, actually, I did not know about this conference much more. I think it would be a 10-minute presentation. I did not know it would be a 30-minute presentation. So I prepared my presentation for just 10 or 15 minutes. So today I want to talk about cyclometalated iridium complexes as phosphorescence emitters. It's all about organometallic chemistry, synthetic organometallic chemistry, and applications. So here I will describe iridium complexes. Iridium complexes is the organometallic complexes in which iridium atom is used as metal, and phenylpyridine type ligands is phenylpyridine type compounds are used as ligands. So final iridium complexes I obtained, and I use its luminescence studies. So first introduction, objective, purpose work, conclusion. First introduction. What are iridium complexes? Cyclometalated. The cyclometalated iridium complexes are those in which iridium atom is the central metal atom, and the ligands used as phenylpyridine type ligands. Here the ligand bind to metal atom in a cyclometallating matter, that is iridium, nitrogen, carbon, 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 iridium. This binds with iridium atom in cyclometallating matter manner, and these complexes can be used as pH sensor, catalysis, anti-cancer agents, oxygen sensors, bioimaging, many applications. There are generally three types. First is iridium L3 type. In iridium L3 type, first iridium atom is used at a metal center, and three types of ligand is used in iridium L2 L type. The all are cyclometalatic ligands are used, but two same kind and one different kind. And in the third one, two is cyclometalatic and other is ancillary. So these are generally three types. So here I use phenylpyridine type ligands. These are the phenylpyridine and its derivatives because they have a high fluorescence as possible value, and the proposed study on iridium complexes therefore designed with the heterolytic iridium complex composed of phenylpyridine, substituted phenylpyridine, and ancillary ligand. Here is ancillary ligand, here is cyclometalatic phenylpyridine type of ligands. And so if we combine different kind of ancillary ligand, we can obtain different kind of metal complexes. If we vary cyclometallic ligand, that is phenylpyridine with diphenylpyridine or benzoquinoline, we can produce a variety of iridium complexes. If we vary the cyclometallic ligand like piconolinic acid or pyridine aldoxine or copperamine, we can produce a different series of this kind of complexes. The history about the complexes. First, Thompson, South California University, that first produced some iridium complexes and used in OLED devices. Then the two type of well-known reproductive complexes are here. In one type, it is a red emitter and it is a green emitter. In the red emitter, this acetyl used as ancillary ligand, and benzophenylpyridine is used as cyclometallic ligand, and this is a green emitter, and the cyclometallic ligand is phenylpyridine. These are two well-known patented emitters. Here is a blue emitter. These two are well-known blue emitter. In the first one is ancillary ligand is diphenylpyridine, and this is picolinic acid. And this was produced by Lumita company in Taiwan. 18 type of this complex is formed. Here the cyclometallic ligand is 10 heterocyclic carbons, and ancillary ligand is acetyl acetone. So Lumita company patented 18 type of these complexes. These two are blue dopants, and ISO lambda max around 405 to 497 nanometer, and this is the highly stable compound. This formed. Then present work, but I will talk about my work. First, I have synthesized the starting material. From the starting material, I prepare my final iridium complexes. Then I have characterized it, and I have applied it in OLED. The characterization technique used to single crystal XRD, NMR, mass, FTIR, and photoluminescence was evaluated by fluorimeter analysis. So first I have produced my starting material. A starting material produced by replacing with iridium chloride salt with phenylpyridine in 2-methoxyethanol. So first starting material is a dichlor bridge compound in which 2 iridium atom and 2 chlorine bridge atom and phenylpyridine atom attached to iridium atom. The dimeric complex is formed of this starting material. It is also yellow in color, and from the starting material, from this starting material, I reacted with any of the 3 kind of ancillary ligand to produce 3 kind of my required cyclometallic ligand. Suppose this is my starting material, I first produced, then I use starting material, I reacted with L1 type ligand. This is a simple ski-based ligand containing benzaldehyde and 2-aminophenol. So first I used starting material and reacted with L1 type ligand, and I obtained this kind of a complex in which chlorobenzene cracks and the ancillary ligand binds with the iridium atom. This is my similarly using these 2 kind of ligand, I produce second and third kind of final iridium complexes. After producing 3 kind of iridium complexes, I have characterized it by single crystal X-ray diffraction. From the single crystal X-ray diffraction, I confirmed the structure of 1 and 2. Here is shown the structure of 1 and 2 by single crystal X-ray slow diffusion method and analyzing by OLX software. Then here is mass. I can obtain the structure of a third ligand. It's don't show single crystal, so I produce its mass spectrum. The molecular mass of the compound calculated is 684 and mass is 684 is shown. So mass is confirmed. Then these are NMR spectra of 3 complexes. From the NMR spectra, I check purity and peak positions are well matched. These complexes generally contain benzylic hydrogen. So in benzylic region, the peak for hydrogen atoms present, if I confirm from NMR, then I go through Dept calculation of the 3 complexes. These are lowest unoccupied molecular orbital and highest unoccupied molecular orbital. From the Dept calculation, I confirmed that in the complex, in metal is lowest populated and the ligand is highly populated. Here, the ligand population is more than metal. Metal is lessly populated. So here I expect a electronic transition from ligand to metal because ligand is more populated and metal is less populated. So the electronic transition comes from ligand to metal. This confirmed from UV. In UV, around 400 to 400 nanometers on peaks obtained. This is due to LMCT band, that is a ligand to metal center band. And from the CB, I calculated that there is 2 oxidation peak. First oxidation peak is due to ligand center, and second oxidation peak is due to ligand center. As the metal center, as the ligand is more populated, so ligand can easily oxidized, then metal is oxidized. So ligand shows lower oxidation and metal shows higher oxidation. Then I produce a second type of dichloride bridge compound. This used benzoquinoline instead of a phenylpyridine. Now I used this kind of a complex with pyridine iridoxine, and I produce a iridium complex, iridium benzoquinoline pyridine iridoxine. So this is a good complex I obtained. I studied its the structure is confirmed from NMR and mass. Its mass supposed to be 670 and 670, there is a peak. So structural confirmation by mass and NMR also. The benzylic positions are well matched from NMR. After establishment of its structure, I have evaluated its fluorescence property. I have this is electronic absorption property EV. With increase in concentration, its absorption property increases, and here also peak obtained due to ligand to metal charge transfer spectra. And upon excitation in this region, I get luminescence spectra. This is luminescence spectra. So increasing concentration, its luminescence increases. So it is a good luminous code. It can be used in OLX. So my complex produced by me can be used in cell imaging activity, OLED, and anti-cancer activity. But I have not studied the application yet. it is undergoing process. Anti-cancer activity is undergoing, and already I will do already activity in the future. So conclusion. So my present work is all about cyclometalated organometallic iridium complexes, and it has application in biological labeling, chemosensor, OLED, and anti-cancer. So I acknowledge to my guides, Dr. Satyanarayana Pal and Hemant Kumar Kisan. This is all about my small presentation, and thank you.
Thank you very much, Kahnu. A very good presentation. The floor is now open for questions. Are there any questions?
So can I ask a question?
Yes, please.
So thank you very much. I'm Yuri Dept from Riga, Latvia. Thank you for your presentation. So could you please tell me what is radiation resistance of this molecule? Because you had explained, you had told about some medical applications, and I'm interested in application, for instance, for the CT radiation dosimetry, something like this.
This can be used in anti-cancer activity. The biotech professor will study about this. We are chemistry and we know how to synthesize, and anti-cancer activity will evaluate by biotech department. They will evaluate it.
So, pardon, can I repeat my question? Yeah, so I'm interested in radiation resistance. If, for instance, the radiation, ionizing radiation is delivered to this molecule, is it stable or not? I mean the luminescent properties.
It radiates in ambient visible region, just electron extension upon excitation of upon incident on light on it, absorbs from visible region and emitting. So it is stable. This is cyclometalated, and here binds to nitrogen and carbon atom, and this is the cyclometalated structure. So it is very stable compound.
Okay, thank you very much.
So.
Thank you very much. Are there any other questions? If there are no more questions, I think I will end this session here. Thank you very much again to all the speakers of this session.